Okay, here we go. Uniformity and arithmetic coming from geometry, or maybe vice versa, I'm not sure. Holly Krieger got her PhD in 2013 at the University of Illinois under Laura DeMarco. She had an NSF postdoc at MIT and is now at Cambridge University, where she has a special position with somewhat reduced teaching so that she can do mathematical outreach, a sort of thing I wish we had more of in the world. Part of this came from her initial success at Numberphile. She was at MSRI, it was the MSRI back then, for a program, and met the guy who makes Numberphile, and she's absolutely charming in those videos. There's over 10 million views now altogether, and she tells me that she partly owes her position at Cambridge to the success of that series. So Numberphile has done something good for the world, maybe many things. Anyway, I've heard Holly before, and I'm looking forward to hearing her again.
All right, thank you very much. Thanks for the invitation to give this talk. Of course, it's somehow this very valuable experience to get to talk about an exciting piece of work that you wanted to get to know anyways, basically. And I should also say maybe a thanks to the people whose work I'm going to speak about, in particular Gao and Habegger, who both gave quite a bit of time to have some chats with me about their results and how they might be explained to a general audience. So I am going to tell you about a series of papers, really, sort of starting with a paper of Phillips in 2013, and with sort of a substantial building up over the past decade of the techniques introduced there, culminating in a couple of papers by Dimitrov, Gao, and Habegger recently in the last couple of years. In addition to some work of Lars Kuhne, which, when taken together, resolve what's known as the uniform Mordell-Lang conjecture. Okay? And when I was thinking about the structure of this talk, of course, when you're thinking, okay, I have some big result I want to talk about, you have sort of two ways to go, right? Do I want to tell you about modern arithmetic geometry and put the result into the context of modern arithmetic geometry, or this piece of modern arithmetic geometry? Or do I want to say, here's a theorem statement, here's some proof ideas, and of course build up the definitions needed in order to do those things? And the funny thing about this proof, or this sort of series of proofs, these works, is that they have this amazing feature. So it's been sort of a long-standing thing in this field that a couple of the very major and deep results, so we'll encounter them in the talk, Falting's theorem and Raynaud's theorem, have more than one proof approach. Okay, and more than one meaning truly different proof approaches. And the thing that's remarkable about the work I'm going to tell you about is that it actually integrates a substantial number of those different proof approaches in the field in order to upgrade them to a much stronger result. Okay, and so in the end, somehow telling you about the statement and some of the ideas behind the proof of the uniform Mordell-Lang conjecture is a journey through this part of modern arithmetic geometry. Okay? All right. So this is Diophantine geometry, or arithmetic geometry. So let's start with the basics, the rational numbers, or the integers. So let's define the algebraic Q-group. No, just kidding, everyone. Bonus points if you know where I pulled this from, by the way. Okay, so no. Just working out a little number theory seminar trauma in a very public forum. Honestly, honestly, I truly want this talk to be accessible. I want us to all get to the finish line together, okay? And in service of that, okay, sometimes I will omit some important words. Some of those words are like smooth, or irreducible, or principally polarized, or level structure, and so on. So please forgive me for that. The other thing is, of course, like, this is a gigantic body of work, and I had to make decisions about what to mention. And so if I do not mention your favorite work, or possibly your own work, if that is not, not the same thing, then please know that I am suffering right along with you, but choices had to be made. All right, let's actually start with the basics. So from the integers, together with their basic operations of multiplication and addition, we can build the rational numbers and polynomials with integer or rational coefficients, okay? And the study of Diophantine geometry or Diophantine questions, Diophantine problems, ask what can we understand about solutions to polynomial equations, okay? So the first thing you might want to ask is, can we somehow tell if you give me one of these polynomial equations, or maybe a system of such polynomial equations, whether a solution exists which has components, say these x1 through xn, can be taken in the integers or in the rational numbers, okay? Unfortunately, this is too hard of a question to ask, as we know by the work of Matiasevich, at least over the integers, so this is Hilbert's 10th, right? We cannot produce some kind of finite time algorithm to answer this question. And so this talk will actually deal with a softer question that is still very difficult about counting, or at least providing an upper bound for the number of solutions to equations of this form. All right, so sometimes, of course, these kinds of equations have infinitely many solutions over, say, the rational numbers. Okay, a classical example is the circle, right? Pythagorean triples, okay? And if you haven't seen before, so these are often presented, I think, when you see them just with some parameterization for Pythagorean triples, okay? But if you haven't seen it before, there's a very nice geometric interpretation of why there are, in fact, infinitely many truly sort of distinct Pythagorean triples, or otherwise said, rational points on the circle, okay? And the reason why there's infinitely many of these things is that, well, there's one of them, for sure. That's my green point here. That's minus 1, 0. And this circle equation is quadratic, okay? And so if I draw a line through that one rational point, it's going to hit the circle in one other place, okay? Well, almost every line, right? And it will hit that circle in one other place, and finding the x and y coordinates of that one other place that it hits will come down to factoring a quadratic equation, which we already know has one rational root, right? And so the other root must be rational too, okay? And so to any rational slope, I can associate the line through minus 1, 0 of that slope and produce a rational point on the circle, okay? On the other hand, very famously, sometimes Diophantine problems have only finitely many solutions, right? So the Fermat curves, here I've drawn for you, I guess, n equals 4. X to the fourth plus y to the fourth equals 1, but of course I can take larger values of n, have a finite set of solutions. In fact, we now know the solution set contains only these so-called trivial solutions where one of the coordinates is equal to 0, okay? And in this case, n is even, so I have 4 of those. Okay. All right, so let's take a little diversion, which is really, it doesn't need to be done at this time, but I want to give you a preview for later when we talk about height functions. So how do we count these sets of rational or integer points, okay? Well, we know how to do this in the case of, say, subsets of the integers, right? Yes, it's an infinite set. However, we have a notion of size on this infinite set, okay? And so we can cut off the integers at some point by fixing some size that we don't want to be any larger than, or absolute value if you wish, and ask how many integers live inside of that bounded region, okay? All right, so I've drawn this picture. Of course, the integers just live in the real line, but I've drawn this picture on the left. It's the same for you and me, just checking. I've drawn this picture on the left in the complex plane. Of course, another way to think about this, if I take the stereographic projection, I can view the complex plane as the points on a sphere with the exception of some point at the North Pole, this point at infinity, okay? And this is a nice interpretation of this notion of size, right? Because we might think in the complex plane of this notion of size as sort of distance from 0. What the sphere interpretation tells you is that we can also think about it as a sort of inverse distance to infinity, which is to say that your size is large when you are very close to infinity on this sphere, okay? And so in this picture, of course, we have sort of down low we have 0, and then minus 1 and 1, and 2, and 3, and 4. And as we go up higher on the Riemann sphere, we get larger values, okay? So we can view the size of an integer as its height on the Riemann sphere. All right. So I use rational and integer sort of flexibly when I'm describing these problems. In this case, we can move from a rational points question to an integer points question simply by homogenizing an equation. Okay? So if, for example, I'm interested in the rational solutions of the equation I have on this slide, so x cubed minus 25x minus y squared equals 0, it does indeed have some rational solutions. I've written one next to the equation. Okay? If I have irrational solutions, I can cancel denominators and produce an integer solution of a slightly modified equation, modified by adding an extra variable to make the equation homogeneous. That is to say, all components have the same degree. Okay? And I can move flexibly, in a sense, between these two perspectives. Okay? But there are a couple of issues. So the first is that when I talk about integer solutions to a homogeneous equation, there's a sense in which there's repetition of solutions if I think of them as coming from rational solutions upstairs. Which is to say that because the equation is homogeneous, if I take each variable and multiply it by some constant integer, I will still get a solution of the equation. Okay? But it's not really a different rational solution, right? The common factor cancels out. Okay? So there's some repetition of solutions here. We can fix this, for example, by requiring an integer tuple to not have any common factors for all the components. Okay? Another problem is that once I've introduced this new variable z, there will be potentially some solutions where z is equal to 0, right? And I can't go backwards when z is equal to 0. I can't divide by 0. And so I will get some points, which are integer points solving the second equation, that don't correspond to rational solutions of the first equation. Okay? This is not really a problem. These are so-called points at infinity. Okay? And so sometimes we will have to consider these things sort of up to some finite list of points at infinity. Okay. All right. So this no common factors thing, let's get a little bit more clear about it. So what did I say? I said that if I have a solution to a homogeneous equation, and I multiply it by a constant, well, a non-zero constant at least, then I get somehow an equivalent solution. Okay? Well, what does it mean to take some tuple of complex numbers, say, or integers or rational points, and consider things to be equivalent if they are multiplied by a non-zero constant multiple? Well, that's exactly like looking at the line through the origin that the point lives on. Okay? And this is the definition of, say, n-dimensional projective space. Okay? So in the previous slide, I was looking at 3 tuples, right, x, y, z. Okay? And in general, if I look at, say, n plus 1 complex numbers, and I identify any 2 of them if they lie on the same line through the origin, okay, then I obtain a space which is actually a bit nicer for various reasons. So it's compact is the main thing. And this projective space, then each element of the projective space can be written as some tuple, so say x0, x1 up to xn, of complex numbers. But the representative is, of course, not unique. Any constant multiple of it will also be a representative, non-zero constant multiple. Okay? Notice, by the way, that 0, 0, 0 is not a point in this space. Right? Okay. All right. So this is the space I want to work in, primarily because of this compactness feature, but also because it allows me to translate everything to integer points questions. All right. So what does it mean to be a rational point of projective space? Well, what it means to be a rational point is that there is some representative with rational coordinates, okay? Or equivalently with integer coordinates, because I can cancel denominators, okay? And how do we count rational points in projective space then? Well, just like in the one-dimensional setting, where my one-dimensional projective space, by the way, is precisely the Riemann sphere, okay, the projective line, our tool for counting rational points has to do with the size of integers when I write this down with integer, oh, thank you, when I write this down with integer coordinates, okay? So if I have a rational point, then there's some representative, say x naught up to xn, where all of the coordinates are integers. But even better than that, there's some representative where all the coordinates are integers with no common factors, right? That representative is what will determine the so-called height of the number. And the height is given here at the bottom of the slide. It's the log max of the absolute value of that set. Notice, by the way, again, they cannot all be 0, and so this is a well-defined quantity. Okay. All right, so we will return to this in detail later. All right, so we're going to focus on plane curves. That is to say, points in projective 2 space which satisfy a particular homogeneous polynomial equation. Okay, just like the example on a couple of slides ago. And the reason, or well, sorry, not the reason, but a feature of focusing on this particular case is that the collection of complex points which satisfy such an equation is actually an algebraic curve, which is to say it's a one-dimensional object, okay, which locally looks like the complex plane, okay, and it's described by polynomial equations. So we did see in the previous talk more detailed definitions from algebraic geometry. I don't want to use them too much, but please don't be worried about the word variety. It just means the zero locus of some polynomial equations, okay? All right. Now, the key feature is that these things are not just algebraic objects, they're also analytic objects, okay? Which is to say that when I take an equation like this, there's a way to identify it up to a finite set of points with some compact Riemann surface, which is to say a compact space that locally looks like the complex plane, okay? And we can move flexibly between these perspectives, though it's not, right, what do I want to say? You need a little bit of machinery to do so, okay? So here's the example from the previous slide. I guess I wrote it in a dehomogenized sense on the left here. So what I've drawn on the left is the real points, right? So, right, this two-dimensional projective plane is, of course, 2 complex dimensions, and so I'm not going to be able to draw there. But I've drawn here the real points, which satisfy the equation y squared equals x cubed minus 25x, okay? I hope that's visible. I know the line is quite thin. On the right, I've drawn what this looks like when I view it as a compact Riemann surface. So topologically, this thing is actually going to be a torus, so the surface of a donut here, okay? Or a sphere with one hole, if you prefer. Okay. All right. So we saw this example for the circle of the existence of a geometric method to take one rational point and construct infinitely many more, okay? So this method that we described, so associating a rational slope to a point on the circle, and again, keep in mind the picture on the left is just the real points, okay? This is actually an explicit description of the identification of the solution set of x squared plus y squared equals z squared with the Riemann sphere, okay? So this example is topologically a sphere. The other example, so this y squared z is x cubed minus 25x z squared, also carries a geometric construction to obtain rational points from a starting point, okay? But it's a different one. So let's say that we start with some rational point. Again, this does admit some rational points. One example of such is the point minus 4, 6, okay? And this is in, I guess, in the xy plane, so my z is 1 in this situation, okay? So my point P is in red on this slide. And again, this is just a visualization of the real points of the curve. And what do? Well, instead of taking lines, sort of arbitrary lines through P, I will draw the tangent line to the curve at P, okay? Now, this curve is essentially an equation of degree 3. The tangent line hitting at P means that we are solving an equation of degree 3 with 2 roots, okay? And so it's going to hit the line, or sorry, the line will hit the curve in exactly 1 more point, okay? You can see that, sorry, I don't have a pointer, but I'll try and sort of match what's going on geometrically. So I've drawn the tangent line through P here, and up here I have 1 more point where I hit the curve described by my polynomial equation. Now, for reasons that I'll make clear in a moment, I'm not going to take that point as my next one. I'm actually going to reflect it across the x-axis. And that's a new point which again for the same reason, because I've got a cubic to solve and I know 2 roots are rational, and the cubic is defined over the rationals, that second point will also be a rational point. Okay? And I can keep doing this, right? So here I've done the same thing to P2. I've drawn the tangent line. I've hit the curve in one other point, which is slightly below the x-axis. I reflect it, and I get this P3, which is slightly above the x-axis. Okay, and we can continue this process as long as we like. And so the point is that, as we saw previously, this curve is actually a one-hold sphere, right, a torus, okay, which is to say that it's an elliptic curve. And our dynamical construction is an example of this rather remarkable fact that an elliptic curve is actually a group. The points of an elliptic curve form a group, okay? And that group law is very easily described geometrically, which is to say that any 3 collinear points necessarily sum to 0, the identity. Okay, so I have a rule for taking 2 points on my curve, adding them together, and producing a third point. Okay? All right. And our iterative process that I was doing, taking tangent lines and then reflecting, the reason I reflected, by the way, is that this was simply the process of taking a point and sending it to the sum of that point with itself. Okay. All right. Now, in theory, this might produce an infinite set of rational points from a single point. But it might not, right? Because it's possible that when I started doing this process, I chose a point which was torsion for the group operation, okay? Which is to say that the point has finite order for the group operation. There's some multiple of the point which is 0. And if I did that, I can end up trapped in this process and stop producing new rational points, okay? So it's not a guarantee, but it's a possibility. So here's a nice example of a trapped orbit under this process, this dynamical process of producing new rational points. All right, so just over a century ago, so this construction, this tangent line construction, the group law and the elliptic curve thing, this is very classically known. So just over a century ago, in 1922, in fact, Mordell proved that the group of rational points on an elliptic curve, so right, I just told you that if you take 2 rational points and add them together, you get a third rational point, okay? The group of rational points on an elliptic curve is actually finitely generated, okay? And I'm not quite sure, is it readable? I think it might be large enough to be readable. I've highlighted here, by the way, I really like the beginning of Mordell's paper here. Mathematicians have been familiar with very few questions for so long a period with so little accomplished in the way of general results as that of finding the rational solutions, blah, blah, blah. He means to elliptic curves, rational points on elliptic curves. But the reason I like this is because from our perspective, it's Mordell 100 years ago, and so we're like, yeah, that's definitely true. But can you imagine putting that in the beginning of your paper? like I'm going to answer something that mathematicians have never been able to even contemplate before, I think. Anyways, all right. So I've highlighted here a phrase in what Mordell is saying. So he gives some equations for these types of curves, okay? But they are all of say, genus unity or genus 1, okay? What he means here is that these curves, when we view them as compact Riemann surfaces, are tori, okay? They have a single hole. And in general, the genus of one of these algebraic curves is precisely the number of holes of the corresponding Riemann surface. So we've seen a genus 0 example, which is the sphere. We've seen genus 1 example, which is the torus. There, of course, you could have 2 holes, 3 holes, 4 holes, and so on. Okay, so there's this topological classification of these algebraic curves by genus. Okay, and the elliptic curves are the genus 1 case. All right, so in the same paper, Mordell conjectured that while we have a procedure, at least potentially, in genus 0 and 1 to produce an infinite set of rational points from one rational point, that in fact, in higher genus, this should not be the case, okay? That higher genus curves have only a finite set of rational points, okay? So I've highlighted here where he actually makes this conjecture. He notes, well, he says it suggests the truth of the following statements, but it definitely took the name Mordell conjecture. And I just want to make the comment here because it's a little bit useful when you're thinking about what is the genus of one of these curves. So he comments in number 5 here that the same theorem, namely the finiteness of rational points, holds for any, or asserts that the same theorem holds for any homogeneous equation of genus greater than unity. Okay? How do I know when the genus is greater than 1? Well, assuming some smoothness conditions, there's actually a formula to compute the genus from the degree of the polynomial. Okay? So if the degree of the polynomial is d, then the genus can be computed by d minus 1 times d minus 2 over 2. Okay? And so in particular, you can take a look at when genus is greater than 1 based on the degree of the polynomial. All right. I have a 2.5-year-old at home, so all questions are, but why? But why? Why did Mordell make this conjecture? What is it about the genus, which is a topological property, that we expect to control the arithmetic, namely the rational points on one of these curves? Okay? The short answer is I truly don't know, because Mordell didn't write down why he made this assertion. But I think we can make a pretty educated guess. There's 2 aspects. One is that this geometric construction, this sort of tangent line construction, or the slope construction that I used in smaller genus, okay, whenever I say higher genus, by the way, I mean greater than 1. This is destined to fail in genus 2 or more, okay? Now, you can sort of halfway convince yourself of this by trying to intersect a higher genus curve with lines. That's definitely not going to give you more rational points because the equation you're trying to solve is of higher degree. You might say, well, let's try conics instead, but it's not going to work, okay? And the reason why is actually sort of what I think is maybe the more suggestive evidence for Mordell's conjecture, which is the fact that there can be no dynamical procedure for constructing an infinite set of rational points, because curves of genus at least 2 have only finitely many self-maps, automorphisms, okay? And so it's not possible to proceed in this way to potentially construct infinitely many rational points from a finite set, okay? So there's a hyperbolicity feature here, which I think is really the backbone of this conjecture. Okay. In 1983, this conjecture was resolved by Faltings in the affirmative. Okay, so there had been some preliminary work, of course. I think probably worth mentioning for later purposes is the work of Chaboty in 1941, who had the idea that we might be able to count solutions to these equations in residue classes, modulo a given prime. Okay. But the full resolution was not until 40 years ago, or 41 years ago now, by Faltings, which is that Mordell's conjecture is in fact true, that a curve of higher genus has only finitely many rational points. Okay, so a little aside, because I didn't want to assume any sort of Galois theory or number theory, just a comment. I mean, of course, when we're solving polynomial equations, say like x squared plus 1 equals 0, sometimes we want to move to a place where we actually have solutions to these equations, like say q adjoin I, right? We want an imaginary number, okay? And we can always solve an equation by extending the field where we allow our solutions to lie, okay? But the key feature about Faltings' theorem is that it doesn't care about finite extensions, that if you take some field extension of the rationals, which is actually finite, the extension degree is actually finite, Faltings' theorem is still valid, okay? All right, so we have this fact that it's a finite set. No matter which genus 2 or more curve I take, the rational points are a finite set. And so the basic question then is, how many elements are in this set, right? How many rational points can a curve of higher genus have? And the first answer is, of course, as many as you like, right? So I've written down a curve of higher genus here. You can compute the genus using your formula if you want. That's why I made it smooth, which has at least 2024 integer points, namely the points where the x-coordinate is an integer between 1 and 2024, and the y-coordinate is 0. Okay. You can be a little bit smarter and cook up some symmetries on your curve to improve this to something like a bound of, if you give me a genus G, I can construct a curve which has at least, say, 8G plus 12. So a linear bound, 8G plus 12 points on that curve. Okay? On the other hand, We know by this rather spectacular work of Katz, Rabinoff, and Zurich Brown, I forgot to put a year, I think it's 2017 or 2018, that in fact a curve of genus G with rational coefficients and a certain assumption that we will understand in a little bit has at most this quadratic in the genus number of rational points, okay? So the example at the top of the page, right, if I want more rational points, I have to increase the genus if I do it this way, okay? But what Katz, Rabinoff, and Zurich Brown are telling us is that, okay, subject to some constraints, we expect that there should be an upper bound on the number of rational points that depends only on the genus of the curve. Okay. All right. On the other hand, there are some very, very unexpected phenomenon. So 8G plus 12 is not anywhere close to somehow optimal, if that's the right way to say that. So there's a very nice example in genus 2, which is due to Stoll, who was searching a family constructed by Elkies. And he found a genus 2 curve, which I've written on this slide here because it's too small to see, I think, in the copy, which has at least 642 rational points. Okay? And I've highlighted here the comment "at least," okay? Because recall, we don't have an algorithm to tell me whether I've found them all. All right? So we can say things about at least rational points, but we don't know whether we've listed them all on this curve. All right. So remember, in the elliptic curve setting, I have a group law, which allows me to potentially produce rational points from a finite set of them. Okay? Now, higher genus curves do not admit a useful group law on their points. But they do embed into some algebraic geometry, which does. Okay? And this is known as the Jacobian of the curve. Okay? And it's an essential construction to all studies, basically, of rational points on curves, and also to explain to you what the uniform Mordell-Lane conjecture is. Let me maybe take this point before I dig into the construction of the Jacobian for the halftime stretch. If you are new to Current Events Bulletin, there is a brief 1 to 2 minute meet your neighbor stretch. So please do that. And we'll return to the Jacobian in a moment. What's that? That was my hope. That was my hope, actually. I really wanted to make it. Gets a little more intense. Really? That's fantastic. Yeah. So what is the target audience? What's the level? I guess it depends on where you are, what level that is. All right. That's great. I'm doing this in as low down here as I can go. All right, I'm going to get everyone back together. Okay, everyone. We have too much to talk about. No more socializing. Okay. All right, so let's construct the Jacobian. There's a couple of ways to do this. So there's an algebraic construction, which is somehow easy to get in your head, but not super useful in life. But okay. The curves or the points on a higher genus curve do not form a useful group, okay? However, they certainly sit inside of a group, which is just the formal group, formal abelian group of points of the curve, right? So I just take any finite sum with integer coefficients of points on the curve, okay? Such a sum is called a divisor, by the way, and this is called the divisor group. Now, this is not as useful as it could be. It's a bit too large, honestly. And also, we'd maybe like our construction that we're about to do to agree with the group law on an elliptic curve when we do this construction to an elliptic curve, okay? And this fails that test, okay? And so I'm actually going to quote Barry Mazur here because it was such a nice way to put this. So the useful generalization is close to this, but it has the advantage that by its very definition, it's seen to be intrinsic, which is to say it only depends on the birational equivalence class of the curve and not upon its embedding in the projective plane, i.e. the particular equations you use to describe it. And moreover, three felicitous miracles occur, analytic, algebraic, and arithmetic, which make it an extraordinarily powerful tool, okay? So this is the key feature, because the questions we're asking about rational points on curves and relating them to genus is about the interaction between geometry and arithmetic, right? The Jacobian is the fundamental tool with which we do this, okay? All right, so what is it then? Well, inside of this divisor group, we can require that the divisor have degree 0, okay? And why might we do this? Well, there's a very natural family of degree 0 divisors, okay? The so-called zeros and poles or principal divisors. And these are the divisors which come from maps from your curve into the projective line, okay, the Riemann sphere. So if I have some non-constant analytic map from the curve to the Riemann sphere, I can define one of these divisors by taking the coefficients to be the order of vanishing of the map, which is to say that it's the multiplicity. I mean, these things are just locally holomorphic functions, right? So this order, if the point is sent to 0, is just the multiplicity of the 0. If the point is sent to infinity, it's the multiplicity of the pole. And if it's not sent to either of those things, the order is 0. Okay, so we get some finite linear combination of points of the curve with coefficients. And we say that two divisors are linearly equivalent if their difference is of the form of one of these zeros and poles divisors. Okay? And the Jacobian of the curve is the group of degree 0 divisors where we identify any two of them if they are linearly equivalent. Okay? So we said all these zeros and poles divisors equal to 0. All right. So here's an example, right? What does the word linearly equivalent mean? Any divisor of collinear points, right? So if I take all of the intersection points of a line with my curve in the plane, is linearly equivalent to any other divisor of collinear points. So here I've drawn an example of a curve of degree 5. It hits each line 5 times because, well, I chose it so that it would do that in the real points, okay? And the sum of those 5 points, say, from the intersection of the first line is linearly equivalent to the sum of the 5 points in the intersection of the second line, okay? This is not hard to see, right? The vanishing of a linear form describes the points that lie on a line. And so this rational map is just the quotient of the linear forms. Okay. All right, so the point is that inside of this Jacobian, we have a copy of the curve, so long as my curve has genus at least 1. And we can see this by embedding the curve into its Jacobian by choosing any base point, say P0, and just looking at the difference of a point P with this P0. Okay, this is some degree 0 divisor. Okay, and one can show that this is actually an embedding when genus is at least 1. And here's the felicitous miracle part. Okay. So this allows me to view my curve inside of a group, right? I've got algebra to talk about. But it also, this Jacobian, has the structure of an algebraic variety. Okay, so I have geometry to talk about. And it has an analytic description as well. Okay, so I will go through this quickly, but it's worth seeing. So because our curve is a Riemann surface, it has a basis of, okay, don't worry if you don't know what I'm talking about. I'll get to the next slide and it will all make sense. The point is I want to do contour integration on my surface, okay? These are the objects I need to do that. So it has a basis of holomorphic one-forms and a generating set for the one-dimensional homology, okay, which is to say loops on the surface. And I can define the period of a cycle to be, so for any of these loops, to be the integral of the form, the vector of integrals of the forms against the cycle, okay? Again, just doing some contour integration, but things locally look like the complex plane, but I have to sort of do it all at once, gluing it together. We define the period lattice then to be this subgroup of G-dimensional complex space, which is generated by these 2G period vectors, okay? So I have some lattice, omega, sitting inside of my big G-dimensional complex space. Okay? And now this Jacobian, which, by the way, is generated by elements which just look like the difference of 2 points, okay, generated as a group. I can take, if I take any difference of 2 points, I can take a path on the curve between those 2 points, and I can define an element of this G-dimensional vector space just by integrating each of these forms along that path. Okay? If I do this, this describes for me a map from the Jacobian into this G-dimensional complex space, which actually factors through omega. Okay? So it's actually a map to the quotient CG by omega. Okay? This is a complex torus. Okay? And the fact is that this is actually a group isomorphism, that the addition on the addition rule on the Jacobian is actually just addition in the complex vector space over on the right. Okay? So that's the analytic structure on the Jacobian. It's not so crucial to understand the details. The point is that I wanted to show you this identification with the complex torus because it's key to what Dimitrov, Gao, and Habegger do. All right. So the point is now we've got our curve. We asked about rational points on our curve. I claim the Jacobian is a key tool. But that's not the only interesting thing that it does. It induces some algebraic structure on my curve. Right? So I don't have a group law for points on my curve because I could add 2 points on the curve and end up somewhere else in the Jacobian, no longer on the curve. But I can ask questions like, when do I have torsion points of the group on my curve? Okay? And the assertion is, or was, and now is a theorem, also 1983, proved by Raynaud, which is that if my curve is of higher genus, then when I embed it into its Jacobian by one of these maps, I can hit only finitely many torsion points of the Jacobian. Okay, so again, a finiteness statement, which depends on the topology, the geometry of the curve. I'm sorry? The Jacobian certainly has infinitely many torsion points. I'm viewing my curve sitting inside the Jacobian, and the claim is that the curve hits only finitely many of. Careful here. I'm not saying anything about rationality. That's a very good point. I'm taking, in fact, any torsion point just as a complex. This is a statement about complex numbers. In fact, you've anticipated my first arrow here. I'm not worrying about rationality in this statement at all. Okay? The Jacobian, because it's a complex torus, what are the torsion points? Well, it's anything which is in the lattice, okay, or which has a multiple which is in the lattice. Okay? So there's a lot of torsion points in the Jacobian, in some sense. And this is asserting that the curve, when I view it inside its Jacobian, only goes through finitely many of them. Okay? All right. But this is nothing about rational points, by the way. This is a statement about complex points, as I've stated it, or algebraic, if everything is defined over Q, say. Okay? All right, so similarly, it's very easy to construct curves with many torsion points in their Jacobian, but you have to increase the genus. Okay? And the record is also by Stoll in this case, but it's a lot smaller. It's 34. Okay, so a genus 2 curve with 34 points. 34 torsion points when embedded into its Jacobian by a particular base point. Okay. But the good news is that there's no at least here. Unlike rational points, torsion points actually can be explicitly computed. Okay, there is an algorithm. All right, so this is actually the picture on my lead slide. These are the x-coordinates of torsion points on a particular genus 2 curve. And the points are torsion if they are both blue and red. Okay? So I've pointed out some examples. There's 3 that I could find on the slide. We kind of knew about those 3. There's probably not any more in this example. But just to give you a description of the picture you saw at the beginning of the talk. All right, so now we are in condition to state what Dimitrov, Gao, Habegger, and Kuhn proved. Okay? So let me define quickly the rank of an abelian group. So the rank of an abelian group is the cardinality of a maximal linearly independent set. Okay? So for example, if I take the subgroup of torsion points in an abelian group, that is rank 0. However, or if I take, say, a finitely generated group, then the rank is the same as the number of minimal generating set. Okay? However, you can be finite rank but not finitely generated. So for example, the rational numbers have rank 1. Okay? All right. So the theorem of Dimitrov, Gao, Habegger, and Kuhne is the following. So if I take a genus, G, and I fix a field, you should just imagine this is Q if you want, or you can think of the complex numbers if you prefer. Then there exists a constant with the following property. For any genus G curve defined over that field and any rational point on the curve, if I embed the curve into its Jacobian via that rational point, and I look at how the curve then interacts with this finite rank subgroup, oh, I think I missed a phrase here. So, sorry, gamma is a finite rank subgroup of rational points of the Jacobian. Then the interaction, so the number of points of gamma which lie on the curve is actually bounded above in size. So first of all, it's finite. Second of all, it's bounded above in size by this constant to a power involving the rank of the subgroup. Okay. What does this have to do with what we've been talking about for the last 40 minutes? Well, in the situation when this field is Q, and the finite rank subgroup is the rational points of the Jacobian, so now I am back in the land of rational points, okay? This is precisely a uniform version of Falting's theorem, right? It's telling you not only is it finite for every curve of genus G, but there's a bound that depends only on these two pieces of input data, the genus of the curve and the rank of the, well, I guess I'm in the special case of rational points, so the rank of the subgroup of rational points, which is controlling the number of rational points on the curve, okay? Similarly, if you take F to be, say, C, or the algebraic numbers if you prefer, and you take gamma to be the torsion points of the Jacobian, so this is a rank 0 subgroup, then you recover a uniform version of Renaud's theorem. Okay? So this encompasses a uniform version. This is what's known as what was known as the uniform Mordell-Lang conjecture, okay, which encompasses both a uniform version of Falting's theorem and a uniform version of Renaud's theorem. Okay. All right. So I'd like to explain, with the time that I have left, 3 of the key insights that go into this. Okay, but I probably will not be able to. So the first is the theory of height functions. So how does the arithmetic, in the case of Falting's theorem, or the algebra, in the case of Renaud's theorem, see the genus of the curve? Right? How do we translate the geometry of the curve into an arithmetic statement? This is done by the theory of height functions. The second is the notion of non-degeneracy and variation of height over the total space of curves of a given genus. And finally, I won't have any time to talk about equidistribution, but I will briefly show you the slide. All right. So the theory of height functions is the classical part, okay? And goes back to work of Wey and Mumford and Vojta as I'm presenting it. So I defined for you the height of an integer point in projective space, right, or a rational point in projective space. And that's the definition in the middle of the slide there. Okay. And I tried to convince you, at least, that in dimension 1, this is a notion of distance to infinity, when I view the complex numbers as sitting inside of the projective line by a particular embedding. Okay? In dimension 2, if I think about taking 2 copies of the C2 and embedding it inside of P2 by mapping xy to xy1, then this height is actually measuring the distance to the line z equals 0, okay, which you can see by the simple computation at the bottom of the slide. What about rational points? Well, actually, it turns out to also be true for rational points, that if I take a rational point in the complex numbers, that height, that log max height, is actually measuring the distance to infinity, but now not just for distance in the normal sense that we were looking at the Riemann sphere, but all possible distances at once, okay? So we have not just the usual sort of Archimedean or Euclidean distance, but a collection of p-adic distances for every prime p. Okay? And this height is telling you something about distance to infinity at for all of them at once. So this fact holds in greater generality. Okay? It holds in higher dimensions. It generalizes to number fields. And you can think of this naive height as a measure of all possible distances of a rational point to a particular subset, namely where the last variable is equal to 0. Okay, under this embedding. The Wey height machine is a procedure that tells you that there is nothing special about xn equals 0. That I can take any polynomial in these variables, okay, look at the set of points which satisfy setting that polynomial equal to 0, okay, so a divisor on my space, say x here, and come up with some kind of notion of a height which measures all possible distances to the vanishing locus of f, okay? All right, so how do we encode the geometry of the curve into this thing? Well, we do this with height functions. So what we do is we take our curve and we look at elements of the Jacobian which are sums of g minus 1 points, okay? So this is a particular divisor on my curve with a quick modification by this so-called theta minus. We can use it to cook up a height function, okay? One of these sort of all possible distances functions, okay? And this height function provides us with arithmetic information about algebraic points on the curve and its Jacobian, in fact, points in the Jacobian in general, and it's encoding somehow the geometry of the curve itself, okay? In fact, we can do even better, which I've done in the blue box here, and modify this definition slightly to come up with a height known as the canonical height or the narrow and Tate height, which actually behaves very well with respect to the algebra, the group law here. So this canonical height on the Jacobian takes a point and outputs a non-negative number, okay, which is 0 if and only if the point itself is torsion, and transforms well with respect to the group law. And even better than that, it can be used to define an inner product on the space of algebraic points of the Jacobian, which means that real geometry is now in play here on this space of algebraic points, okay? And the key feature here, I'm going to have to go a bit quickly with my final slides, I apologize, is that if you make a clever choice of divisor and variety, then you can use the genus of the curve to control that real geometry with respect to the inner product of the algebraic points, okay? So I won't get into the details here, but this was the basis of a second proof of Falting's theorem by Wojta, and then simplified by Bombieri. And this technique is essentially what's followed in basic outline by Dimitrov, Gao, and Habegger. Okay? I shouldn't have Kuhne's name there. His work is not going in this direction. All right. So one key point to make is that if we're interested in uniform control of the number of points in some finite rank subgroup of the Jacobian on the curve, this technique of Wojta actually provides that uniform control if the points have large height. Okay? And so really what these guys needed to do is control points of small height. So this is done using an idea known as variation of canonical height, okay, and a notion of non-degeneracy. So how do we control points of small height, not just on a single curve of genus G, but on all curves of genus G at once? That's what we want to do, right? Well, the good news, first of all, is that we do have some kind of reasonable parameter space to work in, okay, where points correspond to curves of genus G. And in fact, we can look at a sort of total space, which is a space that has the property that, well, first of all, it admits a map to that parameter space, and the preimage of a point in the parameter space is the curve that it corresponds to. Okay? So I want to think of, so this is genus 2 example. I've got this object upstairs, which is sort of sweeping out all possible genus 2 curves. Okay? All right. There is also a parameter space for abelian varieties, say of a given dimension. Okay? And this, of course, includes those which are Jacobians, and a total space upstairs where we have an abelian variety sitting over its corresponding parameter. Okay? Now, we know that we can embed a curve into its Jacobian if we choose a base point. We don't actually want to do this all at once. And so we relate these two objects in a slightly different way by actually taking, say, for example, in m equals 1, 2 copies of the curve. Okay, so I have 2 points on the curve and taking their difference, okay, which is an element of the Jacobian. And I can do this for all the curves at once, right? And the key point is to control small canonical height in this total space, we can actually look at the height of the parameter, okay? So here's an example in dimension 1. So I'm going to let E sub t be the elliptic curve, which I've got on the screen. So y squared is x times x minus 1 times x minus t, so long as t is not 0 or 1. Now, as t varies, this gives me another total space, right? It's a 2-dimensional space, which is sweeping out all these different elliptic curves, okay? And sometimes I can take a point, So if I take, say, for example, a curve in this space, which for each parameter assigns the point 0, 0, then I always get a point of canonical height 0. These are always torsion points, no matter what t is. You can actually see, if you can see in the upper right, I've drawn the real points. The tangent line at 0, 0 is vertical, okay? Which means that the point, when added to itself, gives the identity. On the other hand, if I take a different choice of points for each parameter, I've given an example here with x-coordinate 2, then the canonical height will grow as the height of t grows, okay? So here's a plot by Philip Habegger of exactly this phenomenon, where the x-coordinate is the height of the parameter, and the y-coordinate is the canonical height of the point for that parameter, okay? And the canonical height is growing as the height of the parameter is growing. This is a special case of a theorem of Silverman's about variation of canonical height. And the key feature is that there's a geometric quantity which controls the ratio of these two heights. And if that quantity is non-zero, then parameters of large height cannot have points of small height. Okay? And I'm running out of time, so let me sort of wrap up here. So what Dimitrov, Gao, and Habegger have done is an analog of Silverman's theorem on variation of canonical height, which tells you that points of small canonical height cannot live above parameters of large canonical height. Okay? And they do this with the notion of what's called non-degeneracy. Unfortunately, I have gone a little slow, and so I don't have a chance to tell you more details about it. I will simply end by saying Kuna's input was an equidistribution theorem that is very beautiful. And there are a number of generalizations and further problems which are also very beautiful, and I would be happy to talk about with you later. And I think probably I should stop there. Thanks.